Good afternoon. Welcome to the problem solving session for the course Introduction to Semiconductor Devices, NOC 23 EE82. This is week 10 that we are meeting. Today is September 30, 2023. My name is Amit. I'm a PhD scholar at IISc Bangalore. Let's quickly have a summary of these sessions that we have been talking about. So in the first session, we talked about the material classification in terms of their electrical conductivity, and we classified them in terms of metals and insulators and semiconductors. Then we went a bit to the quantum mechanics. That is, firstly, we saw the concept of de Broglie wavelength. We denoted by lambda uh, is equal to h over p. H is the Planck's constant, p is the momentum, and we also talked about the Heisenberg uncertainty principle. Therein we saw that you cannot determine the uncertainty in position and momentum simultaneously, so there is an uncertainty associated with that. Then we talked about something called a quantum wells. So they are essentially, if you draw potential versus position, right? And so if you draw something like this level is infinity, let's say, and if a particle is here, it's trapped forever, it cannot escape these walls, and we saw that the energy of this particular particle is quantized, and that is peculiar thing in the quantum world. And we saw that, for instance, in classical world, we see the energy is discrete. Quantum world, it's not. This is a symmetrical well, by the way, sorry, asymmetric from 0 to L, let's say, right? On the other hand, if a well is from, let's say, minus L by 2 to L by 2, that is called a symmetric quantum well. This one is an asymmetric because it's only on the right side of the y-axis. Then we saw something called quantum tunneling. This concept we'll again talk about today. So in this, again, if I draw potential versus x diagram, and let's say this is zero potential everywhere except for this small bump over here. Let's call this potential V naught. And if a particle is coming from this direction, we know classically, and this has some certain energy, right? Let's say E naught or V1. So we clearly see that V1 is less than V naught, and it can never escape on the right side of this barrier classically. But quantum mechanically, we could see that there is a finite probability of finding the particle here, because this is a probabilistic world, not a deterministic world, the quantum mechanical world, that is. There's a finite probability, we saw that. And so in this finite probability, we saw that this was happening. So it could tunnel through this barrier, but let's say of thickness T and height V naught. And then we condensed all this information of quantum mechanics into, so essentially what a lattice is a collection of atoms periodically placed. So each atom will have its own, because it's an atom with nucleus and electrons, it will have its own electric field. When we bring them together, their orbitals overlap. There are different ways of seeing that, and then we modeled it through something called a Ronick-Penny model, right? And when they come close together, we saw that their bands overlap, and sorry, their orbitals overlap, and we get something called a band. So by that I mean something like this. So this is your EC, the conduction band, and EV, this is the forbiddance energy gap. So electrons cannot reside here for a semiconductor. And for a semiconductor, this EG is some finite but small value, let's say up to 4, 5, or 7, 8 EV. Insulators have a larger band gap, right? SiO2, if you can recall, it has a much higher band gap. It's than 7 or 8, or usually it's much smaller. Silicon is 1.1 EV, right? And although I'm drawing them flat, actually if I draw the EK diagram, which is also known as the dispersion relation, if I draw the E versus K, this is E versus K. K is your I'm forgetting, K is your 2 pi by lambda. So K is your 2 pi by lambda. Alright, and if I draw this, and this conduction band looks something like this. This is EC, and let's say this is EV. So this gap is your EG, and the curvature of EC and EV respectively give you the effective mass of electrons and holes. EC for electrons, EV for holes. This is an important construct in the sense that all your quantum mechanical effects can now be condensed to this entity called M effective for electrons, separate for electrons and holes, right? Everything can be condensed, so you can forget about quantum mechanics part, at least for this course is concerned, and everything, anywhere you see M, so all the quantum mechanical effects of the lattice and everything will be condensed. So anywhere you see M, you replace it with M star, right? Finally, we saw that we can actually the beauty of the semiconductor is that we can dope it, N type or P type. N means excess of electrons will be there, P means excess of holes is there. Holes is nothing but an absence of electrons, and we denote them in a Fermi level. So Fermi level is something where the finding the probability of an electron is half. So for instance, if you have an intrinsic semiconductor, this means EF will be right at the center. If you have n-type semiconductor, Fermi level will shift to the north towards EC. So this is, let's say, EF for donor, or n-type, not donor, n-type. Similarly, if you have a p-type semiconductor, this band will shift towards the bottom, which I'm drawing in purple over here. I call it p-type of EF. Alright, and this position in the band gap, we can determine the size of semiconductor. That is, this is true for a non-degenerate semiconductor. By that I mean EF minus EC or EV, whatever it is, its magnitude should be greater than or equal to 3 kT. This means doping is moderate, that's all. And only then we could see, analyzing the Fermi function and all, we saw some equilibrium concentration of NC. That is the states, amount of states we have. NV is amount of whole states we have. Ni is the intrinsic concentration. Ni is the intrinsic concentration, that is at a given temperature, what is the concentration of electrons or holes in that particular semiconductor. And we also saw that carrier concentration depends on temperature. For instance, very low temperature, let's say 5 Kelvin or 20 Kelvin, the dopants that you have put, these n-type or p-type, they are not ionized. They have to be ionized to either capture an electron or to donate their electron. These, it's not, it's very partially ionized. So the concentration is very low here. In the extrinsic regime, which is usually the typical semiconductors, is reach around 100 Kelvin or more, and it lasts up to 300 or 400 Kelvin, maybe even more. That is the extrinsic regime. In the sense that the concentration of electrons and holes remains constant. However, if you increase the temperature even further, now the silicon bonds will start to break, and you will have a huge influx of electrons and holes. Generation of electrons and holes, not influx. Finally, we also saw non-uniform doping, and that in the sense that now your EC and EV can be bent. For instance, EC is bent, EV is not. You can have different flavors, and a bend in this is nothing but potential. So, and electric field is nothing but minus grad V. So if you have a slope in potential, you must have an electric field, which is known as the built-in electric field. And now that we have doped the semiconductor, now we can have two things: the transport of electrons. So these are the two mechanisms of transport of charge carriers. First is your drift, that is, in the presence of an electric field, they'll move. So they'll denote move by some drift velocity V, which is mu times the electric field. Secondly, they can diffuse if there is a concentration gradient, high concentration on one part of the slab as compared to the other, the electrons will move. Total current will be the contribution of both, and the mobility and diffusion constant is denoted by D, are linked by something called the Einstein relation. However, in semiconductor, it is not at thermal equilibrium. All this analysis when it's at equilibrium, and it's not at thermal equilibrium, which can happen when you connect to a battery. Carriers will be injected, or you can shine light. There will be generation of electron-hole pair, or they can recombine if there is a large concentration of them. Finally, we condensed all this understanding at semiconductor not at thermal equilibrium in something called the minority carrier diffusion equation. For more details, you can refer to the lecture slides of Professor Naresh or the videos that I have uploaded on my channel. Finally, all the basic understanding of the semiconductor we condensed when we formed a p-n junction. So this is your p-type semiconductor, n-side semiconductor. You bring them together. There's something called form a depletion region, because holes will diffuse from right to left, electrons from left to holes will diffuse from left to right, electrons will diffuse from right to left. There will be a charge carriers here, positive side, negative side, lattice ions. The electric field will be established. So we saw different flavors of p-n junction. This is an abrupt. P suddenly changes to n. There can be linear grading or PIN. Like this is p-type, I stands for intrinsic, this is n-type. This is again a junction. Pn plus means n is highly doped, p is moderately doped, and we invoked something called the depletion approximation to solve the Poisson's equation, and we defined something called the quasi-neutral region. This region you see is called the quasi-neutral region. For this analysis, we found that, and we're using very simple mathematics. We derived the expression for depletion width, peak electric field, your stored charge, and built-in potential. We also saw when it's not an equilibrium, there is something called a quasi-Fermi level. So we saw that Venn diagram for a p-n junction looks something like this. This is p side, this is n side. At equilibrium, this is something like this is the Fermi level. But and this is the built-in potential that I was talking about, the bend in the bends, that is, right? But if you forward bias it, this means you inject some carriers by connecting p side to the positive terminal of the battery. You can lower this barrier, and the carriers will diffuse across the depletion region, and they'll recombine on the n side. The holes will diffuse, right? Reverse side, on the reverse bias, opposite thing happens. The depletion region widens, and the potential barrier increases, and this is closely linked to something called the junction capacitance. Naturally, it depends on the reverse bias and the doping. Then we saw second type of junction, which is the metal semiconductor junction, where we saw on the one side it's your metal, other side it's semiconductor. Again, the same thing, that you have bending and all, but this time barrier is called a Schottky barrier height with some built-in potential. And again, the depletion width. The key difference from PN junction was the mechanism here was not diffusion or drift; it's thermionic emission. And so reverse saturation current concept remained the same, but it had something different dependence with temperature. We saw their comparison also, and we saw there are two flavors of Schottky contacts, that is rectifying and ohmic. Finally, we came to the heart of this course, that is the MOS capacitor, metal oxide semiconductor capacitor. We saw what an ideal MOSFET looks like and its different regimes, that is the flat bend regime, the accumulation, the depletion, and the inversion. These depend on the what kind of gate bias that you are applying. So in the structure looks something like this. If you will recall, metal, this is your oxide, and finally this is your semiconductor slab. Depending on what bias you are applying here, let's say this substrate is grounded, depending on what bias you are applying here, you can have these four regimes: flat band, accumulation, depletion, and inversion. Okay, so we saw what do we mean by strong inversion. That is, although I'll just iterate it very clearly, because this is again we'll revisit. So inversion means, although your bulk substrate is, let's say, p type, but due to application of, this is your metal, this is your, let's say, Vg you are applying. So if you apply a positive bias, you will repel away the holes, excess holes that are there, so you'll something called the depletion. If you apply it furthermore, then what will happen is that the electrons will be accumulated at this junction. So although the bulk is p type, this interface is n type, sorry. This means it's an inversion. And we saw how the electric field profiles look like for different regimes. Surface potential is something, the potential that is I've referred to it here, also known as phi s, right? And this is an oxide, so usually when you apply some Vg, some Vox drops, we solve some numericals. We also saw something called the SOSCAP, semiconductor oxide semiconductor capacitor. So instead of this metal gate, we have a semiconductor gate. So the analysis more or less remains this. Qualitatively, it remains more or less similar. You just have these four different regimes, and rest all was fine. Then we saw the capacitance voltage characteristics for an ideal MOSFET. So if you recall, so this is how we draw. So on left side is your accumulation, and then we enter depletion, and then again this is the inversion that is happening. So this is low frequency, and on the other hand, high frequency curve looks something like this. That happens because the charge carriers here do not have sufficient time to respond to the changing gate voltage over here, and that's why it is not able to rise. So this corresponds to your C aux. This is C versus V. Okay, and yeah, these are the terms we saw. Some non-idealities due to metal semiconductor work function difference, or there can be some trap charges in the oxide. And then we apply this understanding of a MOSFET to create something called a MOSFET. So how does it differ? It's exactly the same. It's just that you have two more pockets here of n plus, and let's say n plus. This is your source, this is your drain. So you have an inversion layer formed by the application of bias on the gate, and how the electrons will flow in this layer, in this inversion layer, is determined by source and drain, right? That's why it's called a transistor, field effect transistor. And again, we saw three different regimes. We'll revise them again today: the linear, the square law, and the saturation. And we saw that in square law, we derived it using gradual channel approximation. We'll see it again today. Saturation was caused due to the channel pinch off, and a couple of terms which we saw is that even when it's turned off, that is when Vg less than Vt, right? Although we expect zero current, but there is some current flowing. It's called the subthreshold current, sometimes also known as leakage current. So there are different ways of putting it. Finally, we saw this is the body terminal. So if you bias the body, you can change the threshold voltage and other things. Okay, so just to now quickly get started for today's class. So we have seen this already. So resistor means potential difference between the two terminals left and right will determine the current flowing through them. And here you can see water, left and right potential is the same, so no current can flow. However, if you tilt it, let's say towards your lift it on the left side, so its potential is higher, water will flow from left to right, and vice versa. Transistor is something different. This means the current flow between the two terminals is decided by the third terminal. So in this case, you have two terminals. So although the left terminal on the bottom is higher than the right, however, this barrier is there, which is not allowing most of this current to flow. Only small amount of water can flow because this barrier is high enough. If I lower this barrier, you can see the left and right is still the same as the middle picture. But if I lower the barrier, more amount of water can flow. Similarly, if I raise the barrier, although the left and right potential is still the same, no water can flow. So this means the current flowing between left and right terminal is being determined by the middle terminal. This is what a transistor means. We saw the MOSFET operation. So the middle part, if you ignore the orange parts, is nothing but your MOS cap, right? And you have gate, oxide, and your body or semiconductor, the different names for that. And if you have source and drain contacts over here of N plus side, you get something called a MOSFET geometry. And this is again a picture from your lecture slides, reciprocating that here. So this dimension is called the width. This will, I'm revising them because this will come in handy again today. This dimension is the width, and the distance between the source and drain is called the length or some. We'll denote it by L. We'll come to L effective later today. Right, and this is the p-type substrate. Yeah, rest is the gate here is the polysilicon that you see over here. The rest of the terminals you can see. The body terminal is not drawn here. We usually, let's call this body. So it's actually a 4-terminal device, right? But usually it's a common practice to short body and source. We saw what body bias can have in the last class, and we saw there were 3 regimes. One is off, that is when VG is less than VT, and second was linear, when VG was greater than VT but VDS was small, and third was VG greater than VT and VDS was large by a certain value called VDS sat, where VDS sat was VG minus VT. We have seen all that, and so this is the expression for VT that you are seeing here, and we have already seen that there's some charge traps, there's non-idealities is the complete expression. And this is that for a long channel MOSFET, we saw this in the last session, right? This is the square law dependence that you see over here. You see this parabola. This is ID versus VG. So increasing VG, you get an increasing ID, but a parabola dependence. So this thing I'm talking about, that ID is proportional to VG squared. I mean this is VG minus VT, but VG minus VT squared dependence, right? And yeah, and VG less than VT is obviously we are not drawn here. It's a linear scale, so it's 0. So all these are for increasing. So this is increasing VG. And how does a ID versus VD look like? So it was given by this expression. So I told you I just tend to remember only this expression. If it's linear, I put VDS very small, so this term vanishes. So we enter the linear regime. For square law, this is applicable. For saturation, I simply put VDS equal to VDS sat, which is nothing but VG minus VT. So if you replace it there, then you can get ID sat equal to mu Cox W by L VG S minus VT whole squared by 2. This is the expression for ID sat, right? Up until now, all the discussion that we had in MOSCAP as well as in MOSFET, right? We had something. Okay, we'll come to that later. This is a very famous whenever you talk about semiconductors in the general public, let's say, this law comes into the picture. It's not effectively a law. I mean, there's no fundamental proof of it, but it's just that we have observed that to just be true for decades in this case. So the question asks the law which qualitatively captures the doubling of transistors every 2 years on a chip. So let's break down this question. So let's say this is a chip of 1 cm cross 1 cm. Let's say I have 100 transistors on it today, or let's say 1970. All right, this is a hypothetical example. I'm just saying it, just putting it for sake of discussion here. And let's say in 1972 on the same chip, 1 cm cross 1 cm, this becomes 200, and in 1974 same area chip, this becomes 400. So what is this law called? So this law is actually called the Moore's law, and this has been standing true. So that's what it's, again, it's from your lecture slides. So the Moore's law says that it's an observation that the number of transistor in an IC, I've just here this example of a chip here, so in an integrated circuit here, doubles approximately every 2 years, right? So this is, and here on your on x-axis is your time, on your y-axis is calculations per second. So it's not transistors per se, you can say, because it's calculations per second. This is something called the speed or the processing speed, and that too as a unit of per unit uh, dollar in this case. Okay, speed over, let's say, money, right? So how efficient, how cheap is it to get the same speed? You can see it's increasing. So what effectively this means is that you are able to get out more speed even though the cost is at a lower cost. So this is the manifestation of Moore's law, that you are able, if you are able to put in more transistors, that means you can form more circuits and at a very simplistic level. This means more functionality or more functions, let's say, or more processing, computing, whatever you want to call it, over the same area. That is, the area is not increasing. That is the reason that you see that for instance 10 years ago or 15 years ago in India there were very few smartphones. Right now every couple of years the smartphone companies launch a new product which they claim to be better, and in certain cases it is, because now high performance gaming can happen on those mobile phones. They heat up, but the performance is getting better over time, and the price tag is not that too expensive. In some cases it's even cheaper if it's a major shift that they were able to make in processing capability. That all has happened due to the fact that we are able to pack more transistors and thus more circuits and more functionality on the same area. There are challenges, but this is what we have observed, and this observation was captured by Moore, and thus with his name, the Moore's law, right? But this does not happen like, you can, when I'm saying that it, you can see on the same area double the number of transistors you are able to put. How is that happening? So what we refer to this phenomena is something called scaling. It's very simple. If you reduce the size of each transistor, you can pack more transistors in the same chip. It's as simple as that, right? So so that was the scaling was proposed by Dennard. In that sense, this is the question. So it's a very simple thing. If you want to pack more chips on the same area, what do? Reduce their dimensions, right? It's very simple. It's like you want to put more pieces of sweet in the same box. How will you do? You'll make the size of each particular sweet piece smaller, right? Same thing is happening here. So what they said, that for a scaling factor alpha, so there's some scaling factor alpha. So what I mean is that, so let's draw a transistor. I'm just drawing the outline. It's a black box for me. So let's say this dimension is L, the length, as this dimension is V. Okay, just a second, let me see. No, okay. So this dimension is L and this dimension is V. Okay, so this is the, let's say, first generation. So for the next generation, what they are saying is that this dimension, now I'll draw in the same box as earlier. Okay, so as to illustrate that how is the scaling look like. So the second one will be something like this. So this will be alpha times L, this will be alpha times V. Third one will be even smaller. So what we are saying here is that if you reduce the dimensions, so that means vertical as well as the lateral dimension. So what will be the correct option? So, and usually alpha is a, as you can clearly see here, that alpha is a quantity that is less than 1. Then only this green box will be smaller, right? So we reduce V is reduced to alpha V is reduced to alpha V. Also L is reduced to alpha L. So we are reducing both the length and breadth. So this option would be correct. Okay, let's demonstrate it in a different way. Okay, so as proposed by Dennard, and we reduce, this is from a lecture slide by the way. So reduce vertical and lateral dimensions by alpha. So what that I mean, so here what do we dimension we have? This dimension L, the channel length. In this case it has become alpha times L. All right, and you can see all other things have reduced. So this is your TOX. Here you can clearly see it's smaller. It's alpha times TOX. Similarly, you can see the junction depths of this n of the source and drain. So this is, let's say, drain, this is source. You can clearly see they have also reduced, right? And some other things have happened. Voltages have not drawn here. We're just talking about the length, the lateral dimensions, that is, right? Lateral and vertical, sorry. We do this, all these things are done, something keeping in mind the constant field. This means that the device on your left and on your right, electric in terms of electric field, they are the same. This means electric field here is the same as electric field here, provided you also scale your voltages. So for instance, you are applying a VDD here, let's say this is grounded, body, let's say, is also grounded in both the cases, and here you apply your VG. So everything you are scaling. So VDD will also get scaled by VDD times alpha. Ground, I mean, zeros into zeros, 0 into alpha is again 0. So all those things are scaling, and when you do that, this is what this scheme proposed by Dennard seeks to say, is that we have a constant field. This means electrically, for instance, if you see your drift velocity is mu times E, what I'm saying is that fundamentally I'm not changing anything. The electron, whatever electron is feeling, in both the cases it's the same. Lateral as well as vertical electric field, we are not touching that, right? We are just playing with the geometry. But there are some challenges that get associated, which we'll discuss in today's class. Today's class, in fact, dedicated to something called the short channel effects, and that's where we are moving to, right? So what this was proposed, and this held true for the most part. We deviated a bit, but it held true for the most part. And this is the most critical of them, of all the three. This is the most critical of the scaling, because this is what which powered the, like, put fitting more and more transistors on the same area of the chip. All right, okay. So okay, by field here I mean electric field. This is electric field I'm talking about. Okay, so next thing what we saw is, next thing we talk about is that this is again a similar thing, again scaling proposed by Dennard. So now here we're talking about supply voltage, which I referred to in the last. This is again from the same thing. Again, the idea is that the field should remain the same, constant field scaling. We are scaling, but field we are keeping constant. So E vertical, electric field vertical, and electric field horizontal. Okay, so electric field everywhere it's the same after scaling. That's what we mean by constant field scaling. So in order to do that, so let's just think that if we are reducing, let's just take a very simple case. So this is your VDD, let's say, okay, and this is again grounded, and this is, let's say, your VD1, and let's say VD2. You want to have the same electric field here, correct? This is now alpha L, right? This is your L. So what is the electric field here? Let's write E1. It will be VD1 minus 0. I'm talking about in the x direction, right? Will be equal to over L. A very simplistic thing I'm drawing, and E2 here would be VD2 minus 0 over alpha L. We want constant electric field, correct? So E1 should be equal to E2. If I do that, you get VD1 over L equal to VD2 over alpha L. This means VD2 equal to alpha times VD1. So voltages also have to scale. This means your supply voltage also has to scale. That was the second point. I've just demonstrated that. Why, from where does this second point arise? It's a manifestation of the first point itself. So we saw that VDD was also scaled down. So alpha is a factor, as I told you, alpha is a factor that is smaller than 1 in our discussion. So alpha, so VD2, so means scaled version should have a smaller VD. Supply voltage should reduce. So VDD should reduce to alpha VD. So this is not correct. This is not correct. Yeah, this is not correct. So one of these three. What about the doping concentration? Here it says it gets increased by alpha. This is primarily due to what we want is that the depletion bits are there. Please remember, when we are applying a gate bias here, there is a depletion bit. The inversion layer is formed along with the depletion layer, right? And it has a depletion width. Also, there is a depletion between N and P. This is a P-type substrate, so you know there will be a depletion layer here, right? There will be a depletion layer here also if it's inverted, and here. So all those considerations are taken care by if you increase the doping by alpha. Okay, so remember, increase by alpha. So that's another consideration. Sorry. So what we have is that VDD will now get reduced. Okay, so these are three options, but concentration should increase, right? So concentration should increase to, okay, so it should be actually N by alpha, because alpha is a factor that is smaller than 1. So only when you divide by alpha it will increase. Okay, so this will be the option. VDD is reduced. We saw that for the constant scaling, and doping concentrations increase because of the fact that, among other things, depletion, which is one of the reasons. So, essentially, it just gets derived from this constant field itself. It's a bit involved, but just that's the way it's work. So, okay, so we have two fundamental things. So these are the fundamental things. These are the, I mean, when you're fabricating a MOSFET, right? These are the things that you can control. These are in your control. What dimensions you want to have, what is the supply voltage you want to with the circuit will drive. Threshold voltage, you know, are determined by, among other things, if you know, VT is nothing but V flat band plus your Q depletion over Cox, and you have Q sorry, phi f, right? 2 phi f. So 2 phi f is nothing but a built-in potential which is determined by the doping of the substrate. Q Cox is determined by Tox and the epsilon of this oxide, the permittivity. Qd is your depletion charge, that again is driven, among other things, by doping and depletion width. Right? Flat band is something you have much less control over, because this is driven by the, okay, this can also you have control, because depending on the metal work function, right? Metal and semiconductor work function difference plus the oxide trap charges. So that also gets scaled. So everything has to be scaled. Every voltage has to be scaled, right? And these are the fundamental things. So if you recall the expression for ID, you have Cox W by L, and you have VT, right? Those terms are there, correct? A function of VT. So so this gets scaled, ID gets scaled. So all other parameters, power is voltage times current. So all those things get scaled by some factors. This is one of the factor that we are asked to calculate, right? Same thing for scaling factor alpha. Total gate capacitance scales as. So total gate capacitance, as you know, is given by this expression. Cg is your gate capacitance. So I'll let me see. No, okay. So let's draw the MOSFET here. So we have this metal, we have the oxide, and then we have the semiconductor. This is your source, this is your drain, and this is your body P type. Source, drain, and this is your body. And here we have this gate. This is your oxide. What is the Cg? The gate capacitance is nothing but epsilon oxide times the area. So so please remember, this is the length, and the width is in this dimension into the plane of the screens. So epsilon ox into A over Tox. This is the Tox that I'm talking about, thickness of the oxide. Very simple, because the inversion layer is somewhere over here. We are assuming that we are applying such a gate bias, that inversion layer is formed along with naturally the depletion layer. So this is the expression. So let's just evaluate that what happens when we scale it. Okay, so let's do that. So so let's write Cg scaled. Let's find that. Epsilon will not change. Oxide epsilon permitted, it's a function of the, it's a property of the material itself. It will not change. Area is given by, so I'll write W scaled into length scaled divided by T oxide scaled. And we know that everything is being scaled by alpha. So we already saw in the I think the last slide, or the slide before that, the lengths get scaled by alpha, right? So W scaled is nothing but alpha times W. Length scaled, so this length is actually later becoming alpha times L. This oxide thickness is nothing but alpha times Tox. Uh, just to reiterate, alpha in this case is less than 1 because we are making devices smaller and smaller. So if alpha is less than 1, a scaled device, right, will have a smaller width, a smaller length, and a smaller oxide thickness. So let's evaluate this. Epsilon ox WL by Tox times alpha square by alpha. So this thing is nothing but your, so this is your original one, WL by Tox. This is nothing but your CG times alpha. So this means what are we saying is that gate capacitance reduces, remember again alpha is less than 1, so scaled gate capacitance reduces by a factor of alpha. This is the analysis that we have performed. So CG reduces, CG does not increase, reduces to alpha CG. This is the correct option. CG reduces to alpha CG. This is just one of the parameters. So there's nothing fancy that we have done here. We know how all the parameters are changing except for permittivity, and we just put in the new values, the scaled values, and then we obtained scaled gate capacitance in terms of the original gate capacitance. So it gets reduced by a factor of alpha. One more exercise similar to this. So again you just imagine this is your gate metal, that is, this is our oxide, and here is your semiconductor. So this is your source, this is your drain, this is your body, this is N plus type. Again this is your channel length L, width is into the plane, and this is your Tox, the oxide thickness. What we are required to determine this time is the delay. So now you might ask, where is the delay coming from? So what's happening is that usually this is the symbol of the MOSFET we had talked about in the lab, and this is, let's say, source, this is grounded. This is usually used to drive some circuit, and it may have some capacitive component. So this is, let's say, C load, and this fellow, this MOSFET, we can model it as a resistor. Alright, so this is an R, so hence this RC delay is coming, and that's what we mean when we say that that the delay in the circuit. So this delay is in first, obviously it's due to the components, the external components, but it is inherently a property of the MOSFET itself. Alright, how is the delay given? So you can just simply, very simple, delay is given by Q by I. Q is a charge that is being stored, let's say, by this capacitor. So essentially when you're switching it, so you're switching between on to off, something like that. Okay, so whatever the charge that is stored in this capacitor, that means the inversion layer charge will have to go to 0 and then come back. So that's what we mean by, denoted by this CV over here, right? And we know and we know the expression for C is nothing but Cox times A. So Cox, when I'm writing Cox here, this is normalized with respect to area. So Cox here, I mean epsilon ox by Tox. Okay, A is your area, which is W times L. V is your supply voltage in this case. Okay, so whatever your rail voltage that is coming. Current we know, so here we are interested in the regime, it's a 2L here actually, we are interested in the regime when we are in saturation. Okay, so we are switching from saturation to off to saturation, and like that is a toggle that we are making. So let's just put all the values, that how will it come. So Cox, I put epsilon ox by Tox times area, which is W into L into V divided by, okay, Cox gets cancelled, so fine, W over 2L Vg minus Vt whole squared. Okay, so this and this gets cancelled, W and W gets cancelled, mu is a constant, so I'm not worried about that. So I'll write it like this: T delay is directly proportional to This becomes L square. 2 is a constant, so I'm dropping it. And this is voltage over voltage square. So I can write L square over voltage. Note, voltage, this voltage as well as these voltages are scaling. Okay, by the same factor, right? This is also scaling by alpha, this is also scaling by alpha. Alright, so hence I can cancel them out. That's why this proportional sign. So L square I know is scales as alpha, right? So I can write is directly proportional to a bad symbol, directly proportional, and voltage also scales as alpha, right? Just a second. Let's hope I've not made a mistake. I think I made a mistake because okay, I equal to dq over dt. So from this, time dimension would be delta q over I. So this is correct. Q is CV, that I have written correctly. C is your epsilon ox times A, which is epsilon, yeah, correct. This is into V. This is the expression for current. Mu C ox W over L Vg minus Vt whole squared. And so T delay will come out to be, so this becomes L squared time V. So T delay, okay, T delay is coming as a factor of alpha. Alright, because this gets cancelled. So T delay, this means T delay gets reduced. So what I can say, T delay scaled is alpha times T delay. So the scaled delay is alpha times the original delay, and alpha means it has reduced. So what we are seeing is that the delay has reduced by a factor of alpha. Alpha is nothing but your scaling factor again. So we see TD reduces, so it does not increase, it does not increase, it does not increase, it reduces to alpha TD, this. And what is the manifestation of this? The manifestation of this is very prominent, in fact. So when we have lesser delay, this means you can switch faster from on to off to on, right? So let's say earlier if you're switching at 100 megahertz, right, that is only your device could support. Now due to your delay has reduced, now you can switch faster, so you can reduce by 100 by alpha megahertz. And usually alpha is what we put as, for the sake of discussion, 0.7, right? So if you divide it by 0.7, this will come approximately 140 megahertz. No, wait, yeah, around 140 megahertz. Okay, so it has increased, the frequency has increased, and remember this happens every 2 years. So just like 5 years down the line, 5 generations down the line, it can increase by even by an order, the frequency. And that is the thing that we're changing. The processing power has increased exponentially, because the processing times have reduced exponentially, and the frequency of switching has increased. That's what we see here, just by the simple thing that the length has scaled, which you see W has scaled to alpha W, length has scaled to alpha L, the voltage has scaled to alpha V. Just by this simple scaling that was proposed 5 decades earlier, some effects are still prominent in front of us. Okay, all right, so till now what we have been talking about is the scaling. That scaling is good, you can pack more transistors, very good. What happens if you scale too much? This is an old saying, excess of too much is a bad thing. So what is the limit up to which we can go, after which we'll start sacrificing? We'll see some effects come into the picture that can hamper our device performance, that deviates it from ideality. So you can just understand that let's say if your length is 1 micron, for this I'll do it in a different color because purple, let's say if your length is 1 micron and you keep on scaling, right? So let's say your next generation L1 is now 0.7 micron, and next generation L2 is 0.5 microns. Let's say 2 generations down the line it's 0.25 microns, and so on. You keep on increasing, right? two more generations down the line is 0.125 microns, right? And then two more generations down the line, L8 is 62 nanometers only. This, when you're entering in this regime, what we start seeing is something called the short channel effects. That means the channel, this L, has become short, and we'll define what do we mean by short with respect to what, because you must have a reference, and we have a reference in this case. This is the problem. So from now, this point onwards, what we'll be talking about is the short channel effects, which came into being, a short channel MOSFETs, which came into existence due to the scaling, due to this aggressive scaling that happened every 2 years, right? And what are the effects that we saw here? So this is a problem associated with that. So the question says that there are two statements. We need to find the true and false of them. Statement 1 asks is that typically the channel lengths for a short channel MOSFET are much larger than the depletion widths of the source and drain junctions, right? So let me just illustrate it with the diagram. So this is your original version. This is from the slide which you saw a few minutes back. So this is your normal one, let's say your long channel, okay, and this is L. So let's focus only on the channel length here, right? And this is your alpha L, okay, which is scaled, and this is what I mean by short. We'll define them right now, right? Let's also draw the depletion region. So okay, so let's say that right now I'm not biasing it. There's no biasing over here, and it is still inverted. So VG is greater than VT in both the cases. All right, and I'm just going to draw the depletion regions now. So there is a PN junction over here, so it will have some depletion, right, which I am drawing like this. Since it's N plus P, most of the depletion will be in the P side, right? Similarly, there will be depletion due to this strain. All right, and there will be depletion due to, if we have inverted that. So I'll draw it in some different color. Let me try purple. So let's say this is the depletion due to the inversion that has happened here, right? Let's do the same exercise here. So let's first draw the depletion region due to the source and drain respectively. So now note that this is N plus plus type, so that even though they are at the same potential here, the depletion is actually will be the same, because this, it has, if we have doped them, doping has been increased for both of them, it will be the same. So let's just same analysis. So depletion widths are still the same as the previous one, as the long channel case, right? And again, since it's inverted, right, so it's inverted, so let me again draw the depletion region, which is over here. So what do we mean by the long channel is that let's say this region is this portion, I'm calling it XS, this portion is XT, okay. So XD and XS are much smaller than L, and we can ignore them. So we can effectively say that all the depletion, that all the you remember the gradual channel approximation, which is the combination, the total charge under the gate is combination of depletion as well as inversion. So here I am just saying that the depletion widths are very small as compared to length. So it's only the gate that is under that is controlling the inversion charge here. Okay, that's only the gate that is controlling the charge profile under it. Here that's not the case. Here XD and XS are not much smaller. They are let's say, I'll not say equal, that will be truly disastrous, but they are of the order of L, the channel length, that is, in this case it's alpha L, because we have scaled it, right? So when this happens, right, that's when we say it's a short channel, short with respect to the depletion widths. Okay, so the first part, the channel lengths for a short channel MOSFET are much larger than depletion widths of source and drain junctions. No, That is the long channel MOSFET. So this statement was true if it were written long here, with it short. So this is false. This statement is false. They are comparable. They're not equal, but they are comparable. They are considerable portion of the percentage of the channel length. Okay. Second part is that the current in a short channel MOSFET shows significant deviations from square law theory. This comes in how this is true, and we'll try to see how it is in the next part. Okay, but this is true for now. So I'll just finish this question. First is false and second is true. So this is correct, and how it deviates from square law theory we'll just see in a minute, right? But till now, if you have any problems in the definition of short channel itself, because this is important, we'll just keep invoking this thing over and over again in today's session, the short channel, short channel, short channel. This is there. So I'll pause a bit over here, and if you have any doubts or you want me to repeat something, you may ask. All right, then let's move forward. Okay, so we'll just now get into what do we mean by the deviation, how it deviates, why it deviates, and how it deviates. Those two questions we'll answer. Right. So this is a problem in through which I'll try to explain the deviation from the square law. So here, this question again similar format, two statements. We need to find true and false. So it asks, statement one says current for a short channel MOSFETs saturates at a larger VDS, right? So essentially we are talking about VD sat here. VDS sat, we're comparing VDS sat of short channel as and long channel. Secondly, they're talking something about the critical field, that what is critical field, how is it related to velocity saturation, that we'll try to see in this problem. Okay, so I'll just revise that the MOSFET operation we have talked about in the last session. So this is your assume this to be a long channel device. Okay, actually in this case it won't matter much. um, it is inverted, so it's a linear regime, so VG is greater than VT. This means inversion has happened, and VDS is very small such that Q inversion uniform. We had seen this in the last. What is VG? So we know that VG now will be there will be 3 or 4 components of it. So there will be a VT obviously, and yeah, and there will be some Vox and some other components are there. We will not go into that, right? Where VT was given by this. Essentially, what's going to happen is the current that is there. The current that is there, right, is given by this. Okay, and what's your Q inversion? Q inversion is nothing but your Cox times your Vg minus Vt. All right. So this is what we had. Vox and all are certain components that we solved a problem in the last session. So Q inversion is given by this. Area we know. Tau is nothing but your time. So essentially the time we wrote it with the help of that, the length divided by the velocity, the drift velocity. And we saw since the field is more or less uniform laterally, so we simply wrote it the Vd as which is the length that it has to traverse. Sorry, Vd is mu e, so this will be mu times electric field. We wrote electric field simply as Vds divided by the length, because VDS is small enough, so this will not change much, right? And you put in all the numbers here, so you got something like mu Cox W by L, right? Because area W into L will come here, 1L will get cancelled from there, right? And Vg minus Vt times Vds. This is the current that we got, and this is true for short as well as long channel. So this is the case. Till here the story is the same. The reason for that is that VDS is small enough, right? Now I'll just go through for the long channel. This part is true for a long channel. Okay, so what's happening is that that we took a differential element dx here, and we saw the profile look something like this. Because VD is now large enough that Q inversion gradually decreases. There is a potential gradient from left to right. Your drain is biased to some higher potential, has significantly higher potential than your source, so that it can form. So on the left side you have more of inversion charge, less of depletion charge, and you see this tapering profile. And again you write the Q inversion as, for a differential Q inversion, as a function of x, that is, we wrote this expression. This is a gradual approximation. Current is again your Q inversion times A over tau. You put in the values. Tau this time is your differential time taken to cross this distance. That's what we write here. Okay, dx, differential distance, over mu, dvx over dx. This is the potential drop, dvx, that I'm talking about. That's how we write this. And we solve this and we got this square law. So this, I repeat again, this is for a long channel, right? What happened in saturation mode? First, let's talk about the long channel. So on your left, I'm talking about the long channel here. The long channel, the VDS is now large enough so that it gets pinched off. So this is from your gradual approximation. What happens if you increase the bias even further? It will look something like this. So I'm talking about this blue line. Now we'll shift, sorry, this blue line. The interface between inversion and depletion that you are seeing will now become something like this. And here, right at the drain, it becomes pinched off. So now this will be the new inversion region at pinch off. At pinch off, right? What's happening here is that essentially is that lateral field, that is field in your x direction between drain and source, cannot increase anymore. If you increase the bias, this point just keeps shifting to the left. We'll talk about this today. But what's going to happen is that this will be of no use, because remember when we talked about, we said Vd equal to mu E. E is electric field, which we denoted by VDS by L, right? The difference in the gradual approximation, that's what we did. So what we are saying here is that even if you the VDS, if you increase even further from this point, you're not going to increase any hike in drift velocity, because L will start to change. So VDS you are increasing, but at the pinch off is the point that matters. There the VDS will remain constant, and that VDS was denoted by VDS sat. Mathematically we did it like this. So we wrote the Q inversion charge again at some distance x, and we saw that at x equal to L, that is at drain, right, this should go to 0. There should be no inversion charge. If you solve this, you will simply get Vx, which in this case is Vx, which is nothing but VDS. This should be equal to Vg minus Vt, which is the pinch off condition. Pinch off condition is when inversion charge goes to 0. If you put it equal to 0, you get Vx at L. Vx at L means VDS, this point, which is VDS, which is Vg minus Vt. This is the definition of VD sat. Different ways of saying the same thing, right? And you put this VDS over here, and thus you get that good old expressions, VGS minus VTH whole square by 2. Put VDS equal to Vg minus Vt over here, you get this. This is a constant value, it's not depending on IDS, hence the current saturates. This is the story in a long channel. Okay, what's happening in a short channel? So remember, we are saying Vd equal to mu E. Here in the short channel is not the case, and we'll see how. For smaller VDS, this expression holds true in a long channel even when VDS is large. Okay, but even for small values of VDS, even 1 volts, let's say, the channel is short enough, the velocity gets saturated. We'll see what do I mean by that. So this is from your lecture slides again. Just look at the bottom curve. So this is your velocity, drift velocity versus the applied electric field. You can see a saturation over here, right? So let's just try to find out. So this is called the critical electric field, this junction, right? This is something called E critical. For every material it is something, after which the drift velocity cannot keep on increasing, even it just deviates from, this is mu E, this is Vd equal to mu E, right? It just deviates from this path. It saturates, just like your current is saturating, right? Current saturation comes from this actually, and we'll see. So in the long channel MOSFET, the saturation is coming from the fact that your the channel has got pinched off, all right, and any increase in drain to source bias will not increase the electric field any further. Okay, so it's not coming that the velocity is saturated. Velocity can increase, but it's your electric field which cannot increase any further. All right, so there's a difference here. This regime is called the velocity saturated regime. Let's try to find out the electric field in a long channel first. So let's say you are applying what, 1.6 volts. Okay, so VDS divided by L. So 1.6 volts divided by L. What is the L that is given for this long channel? This is given as 10 microns, 10 micrometers. Units are centimeter here, so this term will be 1.6. so let's call this as 0.16. 10 micrometer is let me just solve this. 1.6, so 0.16 over 10 to the power minus 4 centimeters. Yeah, so it's 1.6 into 10 to the power 3 volts per centimeter. All right, so long electric field in a long channel is coming out to be 1.6 into 10 to the power 3, which would be somewhere over here. This is for long channel. This means velocity has the potential to go higher. It's not saturated. Let's calculate E short, the electric field in a short channel. Again, VDS over L. Let's apply the same VDS as 1.6 over here. Okay, 1.6 over the channel is 0.18 microns. All right, should have taken it. Okay, it's fine. So it comes out to be this will come out to be around 9. So 9 into 10 to the power minus 4 centimeters. So it's coming out to be around 9 into 10 to the power 4 volts per centimeter, which would be somewhere over here, this point. This is short. So what's happening is that your Vd equal to mu E no longer applies in this for short channels. Why? Because velocity has already saturated. And remember, in the previous all the analysis here, we had directly, how does this come into the picture? This comes into the picture because we have simply written Vd equal to mu E, right? Which is not the case for a short channel. You can see it's saturated. It's not even following Vd equal to mu E. Hence, what happens is that so this is why it does not follow the square law. This answers a previous question rather. Okay, it follows its own law. What law? We'll figure it out later. But the reason is this, that even for modest, so you can see that it's 9 to 10 to the power 4, right? Even if you reduce it by 3 times, even at something like 0.5 or 0.6, it will saturate, which you can see here. It's saturating around 0.6, right? 0.4 or 0.6, somewhere between. So even at very small voltages of less than 1 volts, the short channel will saturate. Okay, and this is happening due to the fact that the velocity, the drift velocity, gets saturated due to the high electric field present in the drain to source region, in the lateral dimension, that is. Okay, so now we see this question. The current for a short channel MOSFET saturates at a larger VDS as compared to long channel MOSFET. This is not true. We saw that VDS sat for short channel is much smaller than VDS sat for a long channel. And we saw the reason was the critical E critical reached for short channel MOSFETs, right? E critical reaches, so Vd cannot increase any further, right? And this causes the problem. So we cannot keep on increasing the the speed at which the electrons are getting transported, right? And current essentially is a flux of your flow of your electrons. So it's like something like q times v. Q is your total amount of charge, v is your speed, so this is the flux, right? So v cannot increase any further, so current will saturate. So and much earlier for a short channel, so the current for a short channel saturates a larger VDS. It's false. This statement is false. Second, short channel MOSFET reaches critical field at smaller applied biases leading to velocity restriction. This is true. This is the analysis that we did, right? The V versus this is VD versus the applied electric field. So we saw that the short channel one was somewhere over here. This was here, and the long channel that we saw was somewhere in the linear regime again, right? And that happened because of the due to the short channels, the direct manifestation of the length of the channel. So first is false and second is true. So this will be the correct explanation. Just to reiterate, how did we analyze the saturation behavior? Both are saturating, but the reasons are different. Okay, in the long channel it's due to the pinch off. It's due to the fact that even if you increase, it's not that the velocity cannot increase, velocity still can increase, but the problem is that the field that you are applying, field across the channel, is not increasing. The reason for that is the pinch off. Even if you increase the voltage, the effective channel length decreases. We'll discuss that more later. All right, so that gets decreased and electric field cannot increase any further. If the electric field cannot increase any further, the velocity cannot go higher and your current will saturate again due to I equal to Q times V. This Q is determined primarily by your gate. This is the inversion charge. This Q is nothing but your inversion charge. This V is being determined by the lateral field. That is your VDS. So this is determined by a VG primarily. This is determined by VDS. So that's the manifestation of, so drain current is manifestation of both of them. All right. So yeah, that is the complete picture. So I'll again take a pause because this is a bit trickier. It might be a bit tricky to understand, but just keep in mind VD equal to mu E. When is that applicable and when is that not applicable? That is your answer actually. The critical electric field is the one that's determining how it's saturating. Whether it's velocity saturated or it's, let's say, for long channel it's pinch off saturated. Okay. Again, another way of asking, representing the same thing, that is story we have discussed, the saturation due to the critical the reaching of the critical electric field in the short channel effect, is this problem. So given below are the two statements and we need to find the true and false of them. So first one is that typically ID in a short channel MOSFET scales linearly with gate voltage VGS. Okay, we have not seen that. We have to analyze whether this is true or not. Secondly, the magnitude of short channel MOSFET is comparable or larger than that of long channel MOSFETs. This we have seen actually. This is not true. How it's not true? Because it saturates earlier. So even in the linear region they can behave the same. However, for the saturation, we see the saturation hits much earlier in a short channel device. So naturally their current will be much lower, right? And we'll see that again. So we have seen this in short channel. For smaller VDS, channel is short enough, the velocity gets saturated because we hit the critical field. So remember, short channel is operating somewhere over here, right? So so velocity gets saturated and thus your current will get saturated, right? How do we express it? We express it this way. Again, the same expression, I equal to Q inversion times the area over the time tau. This is your Q inversion. So it's not depending on VDS, which you expect because it's saturated, right? So VDS can be anything, but if VDS is high enough, that is, right? I'm talking in that regime. So this is this analysis when in saturation, short channel and saturation. Okay, because it's already saturated, so it does not depend on VDS anymore, right? So and tau, right? And tau we can write as the length, that is L, divided by the speed, which is V sat, right? Let's call this velocity V sat. Vsat. And let's put both of these terms here. So this will be I equal to Cox Vg minus Vt times area, which is W into L, divide by tau. Tau is L over Vsat. L and L gets cancelled. What you get is Cox times Vsat, Cox times Vsat times W into Vg minus Vt. So what we are seeing here is the drain current. Okay, this is the drain current. So drain current for a short channel and which is in saturation, right? So the key thing, how this came due to the field that electric, we have assumed that in saturation the critical electric field has already been breached, right? And thus the velocity is a fundamental property of the material, which is Vsat. We put that here. L is the channel length. You rearrange and you see that ID is behaving linearly. Okay, it depends linearly on Vg. So ID in a short channel MOSFET scales linearly with gate voltage. This statement is true. Okay, what about the second statement? Second statement we have already seen. This is again the same picture that I'm drawing here. So if you see here, for long and short, right, Cox, W by L, mu, right, all those things are the same, and VDS and Vg even, right, all these things are the same except for Vt, which is determined by the device itself, among other things the length of the channel, right? So these are the same for both of them. And second thing which is different is wait a second, let me just see if, yeah, that's all. So every physical parameter is the same for both of them, and yet they are different, right? It's saturating. Earlier we have already seen that saturation current for short channel is lower than the long channel, and the reason is that hitting the critical electric field, hitting E critical for short channel, leading to velocity saturation. If velocity saturates, as you can see, I equal to Q times V, current will also saturate, which we are seeing here, right? So that's the complete picture. So this is it's true or false. Magnitude of a short channel MOSFET is comparable or larger. No, it's smaller. This is false. So first is true, second is false. First is true, second is false. Option A. All right. So that is the complete analysis of a short channel MOSFET when compared to a long channel MOSFET, right? The only thing which you have to keep into account is that it does not follow the square law. Rather, it follows linear in this case. The short channel, that is, it does not follow the square law. It follows the linear dependence on VGS, and the reason for that is that the velocity saturation, right? That's the only reason we have been forming an analysis only based on that understanding. Right. Okay, so yeah, that is all, I think. Yeah, okay, another way of power dissipation will scale by how much? I'll come back to this. We know, just a minute. I'll come back to this. Just let me complete this short channel versus long channel thing. Okay, so in a short channel MOSFET, again, as VDS is increased, so what is going to happen? So this is a picture that I have. This is from a long channel picture, but it will help me to answer what we're talking about here. So here, when we're talking about VDS, so what we have is that a channel is being formed, and we have some gradient in VDS, right? This looks something like this. This is the typical curve that we encounter, right? If I increase the VDS even further, what's going to happen is, I've already talked about this, will reach something called this point called the pinch off, right? When you increase the VDS even further, right? And if you increase it even further, what's going to happen is that, as I told, this pinch off point is going to shift further to the left, right? So here at least is covering the complete channel. Here the channel length is not even there. This is the physical channel, L physical. However, the L effective is only this much, right? This is the delta L, that is how it's being denoted. Okay, the question says, in a short channel MOSFET, as VDS is increased, the effective channel length, as I've been telling, keep shifting to the left. You keep on increasing VDS, keeps on shifting to the left. So L effective decreases. All right, so L effective decreases. So this is not correct, this is not correct, this is not correct. What about the total drain current? All right, so let me see if I have some analysis over here. Just a second. Yeah, okay. So we need to talk about the drain current now here. Okay, so what will the manifestation of it shifting to the left will have on the drain current? All right, so how do we do that? In a very simplistic understanding is that we know that ID, let's say in saturation, is some constant K over L, mu and C ox W by L, and all other things I'm not changing them. Okay, let me just do it formally, just a second. Mu and C ox W by L Vg minus Vt whole square over 2. This is the expression that we know, right? What is happening now? We can change only VDS, right? Assuming to be in saturation, assume FET in saturation already. Okay, because the region that we're talking about is this. Pinch off has already happened, we are shifting to the left. Okay, we can change only VDS. So VDS is not even here if you look closely. So you are tempted to say that it doesn't affect. It affects, because this L is not L but L effective. So as you increase VDS, as VDS increases, L effective decreases, which implies Vg and Vtv I am not changing. Mu n anyways I can't change. Cox is already fixed. W is fixed. If VDS increases, L effective decreases. This means ID increases. Again, very simple unitary method. ID is depending on L effective, and L effective will change when VDS changes. So in saturation, if you increase, if you have already hit the onset of saturation, if you increase the VDS even further, all right, your L effective is going to decrease, because this is going to shift to the left, all right, which you can see here. So VDS is dropping, the VDS sat, Vg minus Vt is dropping here. This is a delta VDS, which is VDS minus VDS sat. Total voltage is what? VDS sat plus VDS minus VDS sat, which gives a total VDS, right? So VDS is dropping in two parts. First, across the inversion layer, I mean, not entirely across this portion of the channel, right, where some inversion layer is there. The second part where there is no inversion layer, right? So VDS is split into two parts, just like we saw in MOSFET. The applied voltage was split in Vox and in the depletion and other things, right? Similar thing here, the lateral voltage is being split in the first region where we have inversion and depletion, and in the second region where we just have the depletion, no inversion layer is there. All right, so as VDS is increases, L effective decreases, because this will keep on shifting to the left as we increase VDS. So L effective decreases and your ID will keep on increasing. That's how this is qualitatively analysis, right? So we see ID should keep on increasing, L effective decreasing and ID increasing. So this option, right, channel decreases and total drain current ID increases, right? Now let's do the same exercise quantitatively. Okay, in this question what it says, this was the problem that this is from the last session where I told that we'll discuss in today's class. Okay, so so let's do that now. So here the question says that an n channel enhancement mode MOSFET, this we had talked about. There are two modes actually, enhancement mode and depletion mode, right? You can go through the last session video for more details, right? Is biased at VGS greater than VTH. So if VGS is greater than VTH, what does this mean? Let's not draw this picture. This means inversion has happened. Secondly, VDS is greater than VGS minus VTH. This means saturation. Okay, now here we are seeing the question says considering channel length modulation effect to be significant. That what is this? This is this channel length modulation. Channel modulation means change, so to speak, very crudely. Change in channel length that is happening due to the fact that we are changing the drain bias, right? Channel length modulation. Formally, this phenomena that I described, that we talked about here, is known as channel length modulation. Okay, considering channel length modulation to be significant, the MOSFET behaves as a, so we need to understand how this MOSFET is behaving like. Okay, so let me just start with the analysis that we had, that where we left. Okay, this expression, that is Cn mu ox W by L Vg minus Vt whole square by 2. Okay, let me club now all these terms into some constant, let's say beta. Okay, so now my ID would simply become beta over L, right? Beta over L. Now what I am going to do is that I'll put a differential change delta VDS. Okay, and if I put this, my L will change. So this L is nothing but L effective, only this length. Okay, now I'm changing the L. Okay, so what I do is that, so when L changes, let me do it a bit more properly, just a second. So this is the picture, let's say, when there is the pinch off has just set in. Okay, this is, let's say, onset of pinch off. We have just hit the saturation, and now I'm increasing VDS even further. So what's going to happen? So I can say ID prime, let's say ID prime will be beta over L prime. This is the new L, this, or L effective that I've been calling. I can write this L prime as L, the original length, this total length, minus delta L. This is what I'm calling as L prime. So L prime plus delta L is L. So L prime is L minus delta L. This is at VDS greater than VDS sat. This is at onset of pinch off. These are two different stories. That is at VDS equal to VDS sat. Okay, now what I will take is, I will take L common from here, so it will become 1 minus delta L over L. I just take an L common. Now since delta L, I'm assuming that I'm applying only a small VDS change, differential change, so then I can write this as 1 minus delta L over L to the power minus 1, doing nothing, just, and then I can write it as 1 minus 1 plus delta L over L. All right, so doing nothing, just forgetting what this binomial, yeah, if the delta L is much smaller than L, so 1 minus x, if x is small enough, x is much smaller than 1, then you can write it as 1 minus x. So I'm doing exactly the same, it's the binomial expansion, that is. All right, so this my new ID will be nothing but, okay, this is my new ID. Now this delta L is directly dependent on delta VDS, right? Because remember, what is causing this the change, this change is being caused by the VDS, right? And this beta by L is nothing but my original expression. So let me write that. This will be nothing but your ID, right? And 1 plus delta L by L, right? Another way of writing the same thing, delta L by L, is we denote it by a different parameter when we convert it into VDS, is this. This is the factor that we incorporate. So essentially the change, this is what I am doing, because delta L is being caused by VDS, right? So I just denote this change by this. All right. Now what we are required to find is output impedance. Okay, so Z, I'm using a different color now, green, let's say. So Z out is given by a differential of V out as I out, or since this is an expression given in terms of ID, so I'll simply write delta ID over delta VD inverse. That's it. So what you do is you just differentiate this term, all right, with respect to VD. The first term is a constant, it has no dependence on your VD, so this term will be 0. The second term will survive, that is lambda ID del VDS over del VD. This is the VDS and VD are effectively the same. This is lambda ID. So my output impedance, which is over here, so what we have here is that this will behave, that this has an output impedance. Its magnitude is given by delta ID. We'll see this in a bit more detail in the next slide, I think. But how you can model it is that we already know that in saturation, so I'll draw this diagram here. So in saturation it behaves something like this. This is ID versus VD, right? It's a constant current source, correct? In this region, just look, the current is constant, but it also has an output impedance, right? So how will it look like? So in this region, it's saturation. Remember, the question says we are operating in saturation. This whole analysis was done in saturation, rather after saturation, right? So we have a current source. This MOSFET behaves like a current source with finite output impedance, and that output impedance was given by this delta ID. So it depends on ID. So if you have a high current, right, if a very high current, your delta ID will be very large, correct, and you have a large output impedance. Let me just check that I have not made any mistakes. So it would be V equal to IR. So if I V equal to, yeah, I think we're good. Yeah, so that's how it will behave. So actually what it looks like, what I meant to say was something like this. You see this, it's not flat. This MOSFET 1 is flat, MOSFET 2 has a slight slope to it. This is due to the fact of channel length modulation. So we'll see how the output characteristics, that is VD versus ID, ID versus VD of a MOSFET with channel length modulation, how it looks like. We'll see in this problem. The analysis part we saw in the last slide, the last problem, where first we see qualitatively here. Qualitatively, we saw that after saturation, what happens? We saw that your effective channel length reduces. If the effective channel length reduces, you expect the current to rise, right? Quantitatively, we saw it here. The same problem. We quantified it. How the dependence on VDS look like. Lambda is a factor, right? It looks like how output impedance is lambda ID. Graphically, how it looks like. So this on MOSFET 1 is your device without any channel length modulation. You can see it's flat. Here you can see a definite slope in saturation. So it has saturated, there is saturation somewhere over here or here. But you can see clearly, you can see a slope here. Here is no slope, or very less slope rather, right? So this is a problem with regards to that. So we are given output characteristics VDS versus ID for two MOSFETs. Both have the same VGS at 1.8 volts. W by L is the same for both. Now we are required to identify which is the short channel, which is the long channel. Okay, so let's do that. So what are the assumptions that I'm making for both of them? Right, is that mobility, oxide capacitance, and threshold voltage is same for both. Actually, this is a bit of a stretch. This might not be true. Okay, but at least mu n and Cox, I can assume that they are the same for both of them. Okay, this might not be true. So this assumption might not hold. Second thing, what I see is that by looking at these characteristics, the drain saturation voltage, that is VD sat, VDSAT, I see it is somewhere over here for this, for red curve, right? For blue curve is somewhere over here. I'm seeing the knee voltage, right? It's somewhere over here. It's, you can see there's a curve. Second thing what I'm noticing is the channel length modulation. So channel length modulation, this we saw in the last slide. So there ID was given as ID sat into 1 plus lambda VDS. How will it, if you plot it, it will be like y equal to, this is your x, right, and some constant mx plus c. This is your y, VDS is your x, and your m would be lambda times ID sat, c is your ID sat. Okay, y equal to mx plus 3, straight line with a positive slope, which is like this. This has a in saturation only, so you look only at the right hand side of these red and blue dots. Here it's flat, more or less. Here it's not flat, and we see that only in the, okay, not only the short channel effects. One of the short channel effects is channel length modulation. This channel length modulation rather becomes prominent only when we have short channels. Long channels are not that prominent. Hence, if you are given such kind of a plot of two different MOSFETs, you can clearly see that the channel length modulation is more prominent in the second one. Hence, it's likely to have a shorter channel. Secondly, what we see, the drain saturation voltage, everything else remaining the same, right? If we are grown on the same substrate with the same doping and stuff, right? This much difference of drain currents, of the VDSATs as well as channel length modulation, they give an indication that MOSFET 1 is the long channel, MOSFET 2 is the short channel. All right, what we have is this. MOSFET 1 is the long channel and MOSFET 2 is the short channel. Again, I am assuming that all other things remaining the same, right? The only, just by looking at the plot, the two different things are VDSAT, which are denoted by these dots. Second thing which I can clearly see is the channel length modulation, where there is a slope in the saturation current. It's much higher than there, which is channel length modulation is there, which is more prominent in in the devices with short channels. Okay, so we have identified that first MOSFET is the long channel one, second is the short channel one. The second question in this set asks is to choose the correct option with regards to the electric field at which velocity saturation occurs in a short channel MOSFET. Okay, so we have already seen that actually. So remember, we draw Vd versus, this is your drift velocity versus your E. This was something we denoted as the critical electric field, E critical, beyond which your drift velocity saturates, right? This is for every device, for every semiconductor. So, and we see that only in short channel MOSFETs, what we have is electrons hit VDSAT at smaller VDS. So this is the VDSAT, E critic corresponding, this is VDSAT, and thus ID saturates earlier. And we've already identified that MOSFET 2 is the short channel MOSFET, correct? So MOSFET 2 is the short channel MOSFET. This means in, let's say, E2 must be greater than EC. Electric field in MOSFET 2 must be greater than EC, because it's operating over here, correct? So E2 must be greater than EC. The electric field across channel 2, yeah, this option. All right, this option is correct. Now let's try to do the same analysis for long channel, and we also know that in long channel MOSFETs, E critical is not reached, so thus E1 electric field in the channel for MOSFET 1 must be less than the critical field. E1 must be less than EC. So this is for this. E1 must be less than EC. So E1 must be less than EC. This E1 we already identified as a long channel. Again, just to reiterate, we identified it as long channel due to the fact that it has higher VDSAT, other things remaining constant. Second, it had a very low output impedance, right? It's much more flatter than the MOSFET 2, which denotes it has negligible channel length modulation. So even less than EC, this one, and so these two options are the correct one. Less than EC and greater than EC, yeah. So first and fifth options are correct. Gate also asks these type of questions. So even if you identify just one correct answer, you will not get marks for that. I don't think I don't remember if there's a penalty negative mark for that, but you'll definitely not get full marks. So for questions with more than one correct answer, you have to be thorough. All right. So just make sure that doing half the problem and losing and not getting the marks is when you can secure full marks, just be patient and try to complete the analysis. Okay, so we had long channel and short channel MOSFETs with their critical electric fields which has breached. Yeah, third problem is just simply a visual thing, rather there's nothing to calculate here. So we are asked to find the VDSATs for MOSFETs. So VDSAT we can clearly see when it saturates. So you can see so it saturates somewhere over here. Just take one of the ways of doing it is just to extend the linear line, right, and then you extrapolate it from here. Okay, so it's somewhere between 0.8, because linear will hit at 0.8 rather, and the saturation is hitting over here. So between this is also known as, by the way, knee voltage, right? Knee voltage. So I can see that it's hitting, let's say, 90% of the saturation. So I'll call it has saturated there. So this voltage is between 0.8 and 1.2. So 0.8 and 1.2. So this cannot be correct, this cannot be correct, and this cannot be correct. Okay, so it's 1 volts then. Okay, so they are saying that VDSAT for MOSFET 1 is 1 volts. Let's try to find out for MOSFET 2. So MOSFET 2, is it 0.4 volts? It's definitely not 1 volts, because you can see that it has channel length modulation here, but it must have started to such. If it did not have channel length modulation, it would have looked something like this, the dotted line that I'm drawing, right? So at 1 volts it's definitely not there. This is definitely not correct. 1.8 is definitely not true. So we have 0.6 and 0.4. It's difficult to say. It's not 0.2 because it's still in linear region here. It's a difficult thing to say. Maybe I'll go with this. I'm not confident, to be honest. It can be 0.4, it can be 0.6, because the channel modulation effect is there, so that is complicating the decision. I tried to draw it flat, but it could have been flat from here also. So it's a bit complex. I mean, it's a bit tricky to answer. I'll go with option B. Okay, wait, so I have to go with option, because I eliminate all the other options. It cannot be 1 volts, it cannot be 1.8, it cannot be 0.2. Yeah, and this option was already eliminated, so we are saved that it's 0.4. Fortunate that we were saved. Again, what you can clearly see is the analysis that the identifiers that I discussed in the first part of this problem, where I told that VDSAT is smaller. So we can see that. So VDSAT for a long channel MOSFET, that is MOSFET 1, is around 1 volts, right? But while for the VDSAT for a short channel MOSFET is only 0.4 volts. That is again due to the critical electric field hitting earlier and so on. We have talked about it. Okay, so all right. So now the thing that we are getting into is a bit different. So now we are going into technology regime from the science aspect, where we are talking about the the graduate channel approximation, the channel and modulation, the critical electric field. So that is the physics part of the devices, right? Now when you go into the when you try to apply the same science or physics in the real world, there are many complications that are involved. Remember that the Moore's law said that for every 2 years your T-ox can decrease, right? If you decrease that T-ox to a few nanometers, there's something called, which I told you, which will be visiting again today, is it tunneling, right? The electrons can simply tunnel through the thin oxide, and once you have the tunneling across the gate, this means the gate current is also there. So the oxide is not even an insulator now. So all your analysis, all your science, the physics that you are basing it on, remember, one of the in the ideal MOSFET we had talked about that it's an ideal insulator. That means no current is flowing through that. That assumption will be violated very badly when you have tunneling current flowing through the gate, through the oxide and then to the metal gate. So semiconductor and metal gate, which are there's no flow of electrons or current due to the presence of insulator, that is violated. So all your expressions is does not stand true, right? So that is the problem which was encountered. So it was solved in a rather unique way. So how was that solved? So let's just let me just illustrate. So this is your metal, this is your oxide, metal, and let's say this is your oxide, T-ox, silicon dioxide, let's say, and then you have your source and drain and whatnot. Again the same thing, thicker oxide, that's it, that's the only difference. Rest all remains the same. So let's call this T2, this is, let's say, T1, source, drain, source, and this is your body. It's a P type. So what we are talking about here, so if you recall in your current expression, I'm talking only in terms of saturation. So mu n C ox W over L Vg minus Vt whole square by 2. Let's say Vg, Vt and everything else is remaining same. I'm only interested in oxide. So in oxide, that is, I'm interested in two things. One is the thickness, second is the material. All right. So if I want the same current, let's say in these two devices, mu n is being determined by the semiconductor here, right, which is the same. You can see it's the same body, right? Let's say W and L are also the same for these two devices, right? Vg, same gate bias I'm applying to both of them. Threshold voltage, let's say, is also the same. It might differ, but for this discussion, let's say it's the same. So the only thing that is different is Cox, right? What I want is both of them devices to be the same in terms of drain current, that is, right? So if I do that, so if you put all the expressions here, what you will get is Cox1 equal to Cox2. The rest all the terms get cancelled. So let's put the expression for Cox. It epsilon ox1 divided by T ox1. It should be equal to epsilon oxide 2 over T ox2. Mind you, this device has tunneling or leakage, let's say gate leakage, I would say, because they denote, what do I mean by that? The electrons that are here in the inversion channel, right, they are going through like this to the metal and to the electrode thereafter. Okay, on this device there's no such thing that is happening. Okay, on the second device that I have over here, there's no tunneling. The inversion layer is there, but there's no tunneling. Okay, so how is that happening? So let's just try to solve this now. Epsilon oxide, rather T ox2. Wait a second. T2, this is T, sorry about that. So from this I can write T2 equal to epsilon 2 over epsilon 1 into T1. Mind you, tunneling, as I told in the introduction, depends among other things, on the thickness of this oxide, right? So let's say that epsilon 1 has value of 10, right? Let's say epsilon 1, for the sake of discussion, has value of 10 of so epsilon 1, I'm taking it as 10. The high k, this high k essentially means high epsilon, and let's say this one, epsilon 2 here, is, let's say, 50. All right, let's say T1 is only 2 nanometers, which means, and thus we can see a tunneling is happening, right? Among these things, let's try to find out T2 for these values. T2 will then turn out to be epsilon 2, which is 50, over epsilon 1, which is, where it is, 10, times T1, which is 2 nanometers. This turns out to be 10 nanometers. T2 is 10 nanometers, 5 times higher than 2 nanometers. And among other things, the tunneling probability, the probability of electron tunneling from here to here, depends exponentially on the thickness. I'm forgetting I do not recall the expression for the tunneling probability, but there's an e to the power, it's exponential dependence on the thickness. So when you have increased the thickness, now electrically, remember, first and second device are the same. The only difference is that it has a thicker oxide with a different dielectric material. That's it. The higher, which is known as the high K dielectric, because the epsilon value is much higher, in this case 5 times higher, right? So just by switching the dielectric material to high K, we solve the engineers solve this problem of tunneling. Now if you have 10 nanometers, the tunneling probability reduces, right? So this way the Moore's law was propagated even further, right? Now we could scale it even further. So now it's, let's say, now you can have 10 nanometers of dielectric. Next generation will, let's say, have 7 nanometers. The tunneling probability will still not be as worse as the 2 nanometers here. There are other things, yes, for instance, the oxide trap charges, the insulator trap charges, and so on. Those things are there, but on a first level, the problem seems to have been solved, right? So why I talked, this is just the numbers that I generated, but the reason for this was that to reduce the gate leakage current due to tunneling. So tunneling happens when at less than 10 nanometers or even lower, it becomes prominent, rather I should say that it becomes prominent at those such low distances. So if we can increase the thickness, which we can do if we can obtain the same value of oxide capacitance, if we use a high permittivity material, you can have higher thickness, and the tunneling probability will reduce and your leakage will go down. So that is the correct option. To reduce the gate leakage due to tunneling, we switched to high K dielectric materials, which offer us higher insulator thickness. Hafnium oxide is one such example. Okay, another technology thing. So first thing, the Moore's law scaling, which enabled was solved using the high K dielectric. The second thing was there are a few other problems that we encountered. So in this asks why were FINFETs introduced. So these are from lecture slides again. So on the left you have a typical planar transistor. By planar we mean you have a source over here, you have a drain on your behind this green barrier of gate. Yellow is your dielectric. You can again see the high K dielectric. We're talking about 2011. So high K dielectric was 2007. So this high K dielectric is there. So channel will be formed over here, right? This is the length from source to drain. So electrons will be flowing, this is the positive bias, so electrons will be flowing in this direction, right? So what's going to happen now is that a channel is formed underneath this green region, correct? Now what if there were a way, what was the reason for introduction? To reduce tunneling across the oxide layer? No, that for this we had used your high K dielectric, right? Second option was to achieve more gate control over the inversion layer formation. Now let's compare this with this. Okay, length will remain the same, correct? Now look at the gate, just follow the yellow thing. That's all I need you to do. So here the yellow is controlling only across this width, right? Only the inversion layer is formed only beneath this yellow layer. in the gray region, an inversion layer will form, and the depletion also beneath only this yellow part. Here this runs across all the way across the source, right? It's on three sides, on the left side, on the top, and on the right side. So it will have much more control, not just from the top, how that inversion layer is forming. It will be formed on three sides, right? In this way, rather than having the control, the gate having control only on the top side, on in the tri gate or the FINFETs, this is also known as FINFETs or tri gate. Tri gate means three sides, so left, right, and top, right? In the tri gate transistors, we have more control over the inversion, how it's happening, right? So this option is correct, to achieve more gate control over the inversion layer formation, right? Second thing that you notice is that the length remains the same, but what happens to the width? Width is this height plus this dimension, which you're talking about, thickness of the fin, T fin. This dimension is T fin. T fin. And again this h, height of the fin. So total width will become 2h plus T fin, right? And current, if you recall, is mu n C ox W by L. So in these two, L is the same, right? The only thing that is different is W. And the threshold voltage and all we shift, but we are ignoring them for now. The most prominent thing that is changing is W. So when you increase the W increases, current will also increase, right? So this option, to improve the drain current. And why does the leakage current, so tunneling again is not true in this case. Electric field, again we cannot control. This depends, the critical electric field again depends on the channel length, right? We are not changing the channel length over here. This is L and L. So these two options correct. How does it help with the leakage current? Again, the leakage current is helped because now the control is on three sides, right? So gate and or other way of saying is the high K dielectric with higher thickness is now surrounding on three sides. So the leakage paths, the gate will have more control, so the leakage can reduce. So that's how. So for FINFET technology, these are the two, or rather three main advantages that we gain. More gate control over the inversion layer formation, not just from the top here, but from these sides also. So you can see here we have three fins over here, okay? And to improve the drive current, you can write more fins like this, and each of them will contribute now. So these are in parallel. Note, source is on your, this is source. So source and source, right? And on the other side you have drain. So you can short them electrically and apply VDD over here, and also you can short them like here and ground them, let's say. Okay, this oxide is for insulation purposes. This is not the gate oxide. Okay, this gate oxide is denoted by this yellow, the gate dielectric, that is. Okay, so to improve drive current, because W, if you increase the W at a first level, ID should increase because ID directly depends on W, and the leakage current is reduced again due to some manifestation that the gate is now much more in control, among other things. Okay, so we have some time. Okay, so will we finish this problem and the doubt one of you asked. So again the same about the FINFETs only. So FINFETs offer better electrostatic control over the gate than planar MOSFET. So this is true. So as we know that the gate is surrounding on the three sides rather than just on the top. So A statement is correct. FINFET has lower ion to I of ratio. That is not true. Ion to I of ratio. So this is also known as the leakage, so to speak. Not leakage, but ion over I of is a leakage indicator, I should say. By that I mean that if I draw, let's say, ID in log scale versus, let's say, VG, so there's some subthreshold slope, and then it goes something like this. So let's say this is I off, and let's say this is I on. So depending on how large this swing is, right, how large this ratio is, the better the device is. So let's say if ion is I of, let's say, 10 to the power 8, this means the leakage is 10 to the power 8 times lower. So that's a very good device in terms of leakage. If it were, let's say, 10 to the power 2, that's a very bad device. Means this will look something like this then. Something like this. This is a very bad device. So it's leaking much more. So even in idle state, it will have power dissipation, which we don't want that. For FinFETs have a higher have a reduced leakage, not higher leakage. So has lower ion to IF ratio. No, it has a higher ion to IF ratio. It means lower leakage. So then C is correct, because I told these are the two parameters. So this is also known as the leakage I off that I'm talking about. For a similar operating voltage, planar MOSFETs offer much lower delays than FinFETs. So this is again that was observed among other things, that the planar MOSFETs, no wait, FinFETs have lower delays. Sorry, this is wrong. FinFETs have lower delays than your MOSFETs. The reason again is very simple. We have talked about it when we are talking about delays, is CV over I. So I told you the drive is usually higher, drive current, or the current, let's forget about drive. The current is usually higher because it's dependent on W. So if the current is higher, everything else, the supply voltage remaining the same, and C is primarily your C aux, right? So this C aux is nothing but your epsilon aux by T aux, which I say is the same for both technologies, planar as well as FinFET. C aux will not change, V will not change, only I is the determinant. So if I is higher, delay is lower. If the delay is lower, as we talked about, the switching can be faster, right? So that's why FinFETs have slightly higher operating frequencies, right? Or they offer lower delays than MOSFET. So this is incorrect. Planar MOSFETs have higher delays than FinFETs. So yeah, so that completes our analysis for FinFETs.